at concave mirrors, and we're going to look at when the image is at the focal point. So here we have our spherical mirror for our concave, and this is essentially where the center would be, and the focal point from our first formula is halfway from the center to where the image of the mirror is. Now it's hard to see with the whole circle, so we'll get rid of that so it's a little easier. Okay, and in this example, we're going to have an image that is directly at the focal point. So let's say we draw our image here. Okay, so what that means for us is we know that actually I should go over these, sorry. Of our equations, we have our focal point, our distance of our object, distance of the image, height of the image, height of the object, and obviously the magnification. Here are our formulas for them. If you're unsure what each of those stand for, you can pause here and just kind of go through each of them. Okay, so anyways, now that we have that information, our object in our mirror is going to be exactly where the focal point is at this thing. So the distance of our object, okay, so distance of our object is going to be, and since the center is 6, we know the focal point is 3 according to our first formula. Center is 6 is equal to 2f. That means f is equal to 3, and the distance of the object is at the focal point, therefore it's 3. And we're going to say the height of the object is 2 units. Okay, so everything will be in units here. With that being said, normally this is how the image would work. We would have the image, the top of the image going to the mirror and then reflecting back through the focal point. Okay, but now we can't have, in all of our other examples, we normally had our image go through the focal point and then reflect back parallel. But we can't have that happen because that would be a vertical line going downwards. So instead what's happening is the top of the image is heading towards the principal axis of the mirror, and then it is bouncing off at the same angle as the other light ray for the image, and then we have what are considered parallel lines here. So because they're parallel lines, there is no image here. Okay, so let's see if we can kind of mathematically show that idea. So we'll take our second equation. Okay, our second equation states 1 over the focal point, we know the focal point is 3, is equal to 1 over the distance of the object, which is 1 over 3, plus 1 over the distance of the image. The distance of the image is unknown. Okay, so we need to isolate for distance of the image. So we bring 1 over 3 over, it becomes, we subtract by 1 over 3 is equal to 1 over the distance of the image, and we get 0 is equal to 1 over di. Okay, and if we take a look here, we would normally kind of do a cross multiplication. We'd bring di over and then divide by 0, which doesn't really happen, but I'll show you this mathematically. Say we had di multiplied by the idea of 0 is equal to 1. Distance of the image is 1 over 0. This is undefined, it doesn't exist, and that's exactly what we have here, an image that doesn't exist in this point. Okay, so that is the case when our image is at our focal point. When our object is at our focal point, there is no image because of the parallel lines.